Alright, hello class. In this video we should be finishing section 3.2, which is about open and closed sets. And we are going to actually get to what I consider to be the real definition of the real line. How we can actually finally make that jump from the rationals to the reals. I mean, we've done it before with talking about it in terms of supremums, which I think is a little out there. I think with closed sets and what we're going to talk about today, and limit points and whatnot, we will have a much more concrete feeling jump from the rationals to the reals. So let's actually start talking about it. So we know, of course, that the rationals are contained in the reals, and then I'm going to let x be any element in the reals. Okay, any real number. All right, then my claim is that x is a limit point of Q. Alright, so and here's my claim. To prove this, we're just going to let epsilon be greater than 0 and be arbitrary. Okay, then before I start on this, then consider the epsilon neighborhood around x. Okay, which we call v sub epsilon around x, also known as x minus epsilon to x plus epsilon. All right, now by the denseness of Q, okay, there exists a rational number between x minus epsilon and it should be strict inequalities there, but by the denseness we can find a rational that lives between x minus epsilon and x plus epsilon, and we can do that for any epsilon. Okay, so and we can do this for any epsilon greater than 0. Okay, so in other words, for all epsilon greater than 0, there exists a Q in the rationals such that Q doesn't equal x and is in the epsilon neighborhood around x. And that basically is employing the original definition of limit point. So this implies that x is a limit point of Q. Okay, now the important part of this is that x was just an arbitrary element of the reals. So this means every real number is a limit point of Q. All right, so what this actually means is that the reals actually end up being Q, and then we would just union all of the limit points of Q. So this would be Q union L, where L is the set of all limit points of Q. Okay, so I feel like this finally answers our original question, that when we started with the naturals, to jump to the integers, we added in subtraction. Okay. Then, to get from the integers to the rationals, we had to add in all the divisions. Now, to get from the rationals to the reals, we add in all the limits, right? So any sequence that would exist in Q, we take all of those limits of all of those sequence and add them in, and that gives us the reals. Okay, so it's the limits of the sequences that actually make up our real numbers, which I find a very fascinating thing. All right, now this also gives us a new or different way to talk about denseness. So I'll just say this gives us a different way to categorize, maybe that's not the right word, it gives us a new way to think about denseness. So we know that the denseness of the rationals in the reals is that between any two real numbers we can find a rational number. We also know that in between any two real numbers there's an infinite number of rationals. Okay, so let's note some of these things. So first, we know between any two real numbers, so between any two reals, there exists a rational. And it goes much further than that. You can take this idea and then say that between any two reals, there exists an infinite number of rationals. Okay, and that idea and what we just talked about here gives us the final, maybe not the final, but the next way we can think about the density of the rationals in the reals, and that leads us straight to Theorem 3.2.10. Okay, so the density of the rationals in the reals basically says for all x in the reals, there exists a sequence of rational numbers that converges to x. Okay, i.e., there exists an r sub n in the rationals such that r sub n converges to x. And we can do this essentially, since for all x, x is a limit point, therefore we can create a sequence in the rationals that will converge to that real. And we can also make the distinction that, you know, that none of them can actually equal x, and that comes from it being a limit point. Okay, so we can actually completely determine density of the rationals in terms of sequences. In fact, we can create a lot of the ideas we have about analysis completely in terms of sequences, which I find to be a pleasing way to do things, since sequences and the limits are so important to calculus, so important to analysis. To me, it just makes sense that you would want to define as much as you can in terms of sequences and limits. All right, so what we just did here, where we took all the limit points of a set and created a new set with it, that's actually what's called the closure of a set. Okay, so let me give the official definition of that, but essentially the closure, it's actually exactly what it sounds like. The closure, if you think about what you're doing, you're creating a new set out of another set, but you're forcing it to be closed. All right, so given a set A, which is a subset of the reals, we're going to let L be the set of all limit points of A. Then the closure of A is defined to be this set here. We use a bar for this. So A bar, the closure of A, is equal to A unioned with its limit points. Okay, so basically A bar is the closed set that we create by just taking all the limit points of A and adding them in. Okay, an example of this would be one of the previous examples we looked at, which is just our 1 over n, where n is in the naturals. Okay, this set was not closed. We talked about that before, but its closure would basically be A union 0, which we discussed is its only limit point. Okay, so that's what the closure does. It just unions in any limit points. Also, based on what we just talked about regarding the rationals, turns out that if we take the closure of Q, we get R. Now, there's a lot of, I remember when I was first learning about the closure, I couldn't wrap my head around it. Here's basically what it is. If you have an open interval and you take the closure of it, it basically adds in the endpoints. All right, now that's only if you're talking about an interval. But say you have something like 0 to 1 closed on one side. If you take the closure of it, you get 0 to 1 closed. Okay, so it basically just takes all the limit points and adds them in to make it a closed set. All right, so this naturally leads us to Theorem 3.2.12, which basically says that for any A in the reals, the closure A bar is a closed set and is the smallest closed set containing A. Okay, so the part that is actually easier to prove here is that it's the smallest closed set containing A. It may seem kind of obvious that the closure is a closed set. The problem that could arise, okay, so what we have to make sure about is that L, the set we were talking about, which is the set of all limit points, doesn't create extra limit points, okay, not in itself, basically. So we just need to make sure that the set of limit points doesn't itself have limit points that are not in L. Okay, so that's really going to be the trick to proving this particular theorem, because it kind of, the part of it making A close, like adding in anything that isn't in A that's not making it close, of course that should make that part close. But if L has any extra limit points itself, we would run into problems there. So let's see if we can go about proving this. Okay, to start with, we'll start with the following claim. All right, our claim is that L is closed. And where, let me just redefine it, where L is the set of all limit points of A. All right, so we're going to set about proving this claim here that L is closed. And to do so, we're going to start by, we're going to let X be a limit point of L. All right, now, to show that L is closed, all we need to do is show, all right, here's our want to show, X is in L. So I'm not actually supposing X is in L. I'm just supposing that X is a limit point of L. And we want to actually show it's in L. And if we can do that, since X is arbitrary, it will show that L is closed. And we might get something a little more while we do this as well. So if X is a limit point of L, then I'm going to let epsilon be greater than 0, and then this tells me that the epsilon neighborhood around X intersects L at some other point than X. So here I'm just employing the definition of limit point, right? So I'll just write it as the definition, but then V sub epsilon, the open, or the epsilon neighborhood around X, intersects L okay, at a point other than X. Okay. In other words, right? In other words, there exists a little l in big L such that little l is also in the epsilon neighborhood around X. Okay, now L itself, little l, and let me write it like this, note that little l is a limit point of A. So every epsilon neighborhood around L has to contain a point of A. So here's how I'm going to utilize this. If I look at, say, a number line, okay, and so let's say this is X, and since it's a limit point of L, I know for any epsilon neighborhood, there's going to be an L here, okay? But L is also a limit point of A, so any epsilon neighborhood, around this L is also going to contain an A. So if I put an epsilon neighborhood, okay, around L, I should get an element of A. Okay, so what I want to do now is just choose an epsilon small enough so that the epsilon neighborhood around L that will contain A will also be contained in this original epsilon neighborhood around X. All right, so what we can do is take an epsilon. Really what we want is something smaller than, say, the distance between L and one of the endpoints, the distance between L and X, and the distance between X and the other endpoint. But that would only be true if L is on this side of X. If it's on the other side of X. Okay, so the way it works here is I need to pick the smallest distance I can, and if L is on the other side of X, for example, okay, then the distance between L and this endpoint is going to be less than the distance between L and X and L and the other endpoint. So what I need to do is basically take the minimum between the distance between L and X and L and the endpoints, because one of those is going to be the smallest, and then even if I'm still unsure, I could just cut it in half. So if we take, instead of epsilon, let's call it lowercase delta. We'll let delta be the minimum of the distance between L and X, the distance between L and the endpoint. So that's going to be L minus X minus epsilon, and then the distance between L minus X plus epsilon, right? So we're just going to take the minimum of one of these three, and I'm just going to go ahead and divide it by 2. Right? Now, since L is a limit point of A, okay, there exists an A in the delta neighborhood around L. Well, the delta neighborhood, by definition, okay, this tells me that A is in the delta neighborhood around L, which is contained in the epsilon neighborhood around X. So that means A is in the epsilon neighborhood around X, and since epsilon was arbitrary, this implies that, well, X is also a limit point of A. So this implies X is a limit point of A, which further implies that X must be in L, since L is the collection of all limit points of A. Okay, so what this basically says, this actually gives us a lot. One, this implies L is closed. But it also gives us more. It also implies that A bar is closed. Okay, and that's because, right, since if x is a limit point of a bar, then if it's, well, okay, let me put it this way. If it's a limit point of a bar, then that means it's a limit point of A union L. So that means x is a limit point of either A, L, or both. And in all cases, x is a limit point of A, implying x is in L, implying x is in a bar, and there we go. Okay, so there's the proof of the first part. So let me just put a check mark there. Right, because if x is a limit point of A, well then it's in L. We just proved that if x is a limit point of L, it's also a limit point of A, which means it's in L. If it's a limit point of both, well then both will hold true, and you know, in either case, any limit point of a bar is inside of a bar. All right, so a bar is closed. So really, in proving, all we had to do was prove, if we go back up, all we had to do was prove that L was closed. Proving L was closed in this manner essentially did this for us. Okay, so now to prove that A bar is the smallest closed set containing A, that's actually a little simpler. So let F be any closed set containing A. Okay, well, since F is closed, it contains all of its limit points. Right? And since it contains A, F must also contain all of A's limit points. Okay? In other words, L is contained in F. So A is contained in F, L is contained in F. This means that A bar, which is A union L, is completely contained in F, thus proving that A bar has to be the smallest closed set containing A. Okay, therefore A bar is the smallest closed set containing A. Okay, there are some interesting things that come about our definition of closed set. The first is, recall that Q bar, Q closure, is equal to the reals. And based on this theorem that we just proved, this implies that R is closed. We also get that from the previous theorem, which basically says that for any real number, there exists a sequence in the rationals that converges to it. So, in other words, this is also true. R is also closed because for all x in the reals, there exists a sequence in R such that it converges to x. I mean, the quickest one you could think of would just take x plus 1 over n. This will converge to x, and if I call this, let's say, a sub n, and each a sub n will not equal x. All right, so in other words, every x in R is a limit point of R, and every limit point of R is in R. Okay, so as I was saying in the previous lecture, R is closed under limits. Right? Well, this means that R is both open and closed. Okay, which is strange. The empty set is also both open and closed, and we'll have a good way to describe why in just a second. Okay, but thankfully these are the only two sets where that's true. And again, we'll explain. We'll have a good way to explain that in the next theorem. Okay. Another thing that might seem a little out of whack is that basically any finite set is going to be closed. So any finite set will be closed. Well, if you think about why, if say the set A equals say A1, A2, A3, on up to AN, there's no limit point here. Every point of a finite set is an isolated point. So every AN, every A sub k in A, for k between 1 and n, is an isolated point. Therefore, A has no limit points. Meaning, A contains all of its limit points because it doesn't have any. Okay. You can say the same thing about the empty set, right? The empty set has no points. It has no limit points. Therefore, it contains all of its limit points since it has no limit points. Okay, that's why the empty set is closed. Okay. All right, now we know Q is not closed because it has plenty of limit points that don't exist in it. All right, so it has plenty, in fact, an infinite number of limit points not contained in it. Okay, but what about, say, the naturals? Well, the naturals has no limit points. All right, there's no sequence in the naturals that converges other than ones that repeat themselves over and over and over again, right? You could take the sequence 2 over and over and over again, but that does not make 2 a limit point. So n is all isolated points. So n contains only isolated points. Okay, so n is closed. That might seem really strange. I'll have another way to explain that when we get to the next theorem, okay, that we'll talk about. But this also implies that the integers z is closed. Okay, which is maybe not what we would originally expect, but it just comes from the fact that every point is an isolated point. And if every point of a set is isolated, that means the set itself has no limit points. If it has no limit points, then it vacuously contains all of its limit points. All right, as I mentioned before, open and closed are not necessarily opposites of one another in the way that if a set is not closed, then it must be open. They don't relate to one another in that way. How they relate to one another, though, is that it's through complements. So if you remember, a complement is the set of x, all x in R, such that x is not in A. Okay, so what this theorem is saying here is that a set O is open if and only if O complement is closed. Likewise, F is closed if and only if F complement is open. So that's how they relate. It's not that if you're not open, you must be closed. It's that you're only open if your complement is closed. And you're only closed if your complement is open. So, for example, right, R is open and closed. R complement is the empty set, which means that since R is open, its complement must be closed. R is closed, its complement must be open. This implies the empty set is open and closed. Okay. Another way to think about this, consider this set. Let's say I is the interval 0 to 1 closed. Okay. Then I complement, well, that's going to be everything not in this interval. So that's actually going to be negative infinity to 0, open, union, 1 to infinity. As we proved previously, the union of open sets is open. Therefore, we have that I is closed, I complement is open. Let's say we have J. Okay, J, let's say, is the open set 0 to infinity. Okay, well then J complement, okay, well J complement is going to be everything not in here, so it will be negative infinity to 0 closed, because 0 is not in this set, but it is in this set, so this must be a closed set. J complement is closed, J is open. Now, here's the interesting bit. We know what n looks like, the naturals. It's 1, 2, 3, 4, 5, etc. N complement is going to be everything not in this set but in the reals. So it's going to be all your negative values all the way up to 1, not including 1. Then union 1 to 2, union 2 to 3, union 3 to 4, right? So essentially, if n does 1, 2, 3, 4, on and on and on, then n complement is all these open intervals in between. Okay? And as we proved in one of the earlier videos, the countable union of open sets is open. So n complement is open, therefore n must be closed. And we can use this same example, right? We can use the same example for n, or not n, but for z. Okay? All right, now I don't have enough time to prove this theorem in this particular video, so this one will go another lecture video, but that's all right. So definitely enough brain melting for one video, so I will catch you all on the next one where we will prove this theorem dealing with complements. And that will actually be very helpful as we go forward, because sometimes it's just easier to show that the complement of the set you're looking at is open or closed than it is to show the set itself. Okay? All right. So with that, I'll catch you on the next one.